We have these incredible, absolutely sprawling maps of all the matter in the universe, and hidden inside them are the deepest secrets, things like dark matter, dark energy, how everything even came to be. But for decades, actually reading these maps has been a huge problem. Now, though, a new kind of AI is completely changing the game. It's turning the dreaded black box of machine learning into a transparent glass box that we can finally look inside. So let's get into it and figure out how we can actually read a map of the entire universe.
Okay, so picture this. You're trying to understand a massive crowd, like at a concert or a festival, but you can only look at it from an aerial photo. You can't talk to anyone. All you have are the patterns they make from way up high. Well, that is the exact problem cosmologists are up against. They've got the map, but how you pull out the real story of the cosmos just from looking at where all the galaxies and matter are.
All right, so here's what we're going to cover. We'll start with how we read the cosmic map now. Then we'll look at the two big approaches people have taken, what we'll call the statistician versus the oracle. After that, we'll dive into this new glass box AI, put it to the test, and wrap up by talking about what this all means for smarter science.
Okay, so we get these just incredible maps from surveys like the Dark Energy Survey, and what they show us is the distribution of all the cosmic matter, which has been shaped by gravity over billions and billions of years. I mean, all the information, everything about the fundamental rules of our universe, it's all encoded right there in those patterns. The big challenge, though, it is really tough to get all that information back out.
So the traditional way to tackle this is with a tool called the two-point correlation function, or 2PCF for short. It's a classic, it's powerful in its own way, but it's also pretty simple. What it does essentially is it just measures the average distance between any 2 points, say 2 galaxies on the map. So if we go back to our crowd analogy, this is basically like knowing the average distance between any 2 people. It tells you if the crowd is generally dense or sparse, but, well, that's pretty much it.
And yeah, that is the big problem. Just knowing the average spacing means you miss all the good stuff. You don't see the little groups of friends huddled together, or the long snaking lines for the food trucks, or the big empty patches of grass. And in cosmology, that means we're totally missing the huge galactic clusters, the long filaments of dark matter that connect everything, what scientists call the non-Gaussian information. That's where the real story is hidden.
So to try and get at that deeper story, scientists have basically come up with two main strategies. And it kind of helps to think of them as two different characters. You've got the meticulous statistician, and then you have the powerful but kind of mysterious AI oracle.
Okay, so on one hand, you have the statistician. This method is super careful, it's precise, we can understand it completely, we know exactly what it's measuring every step of the way. The downside, it is brutally slow. On the other hand, you've got the AI oracle. This is your standard neural network. It is incredibly fast, super powerful, but it's a total black box. It spits out an answer, but you have absolutely no idea how it got there. You just have to trust it.
So let's break down how the statistician actually works. It tries to build up complexity. It starts by looking for pairs of points, right? Simple lines. Then it looks for triangles. That's the 3-point function. After that, it searches for quadrilaterals, the 4-point function, and you could keep going. Now, each one of these steps adds absolutely crucial information, but the cost, the amount of computation needed, just explodes. It becomes astronomically expensive. Honestly, trying to go beyond the 3-point function is, well, it's pretty much impossible with this method.
And this right here really gets to the heart of the problem with the AI oracle. See, in science, it's not enough to just get the right answer. You have to understand why it's the right answer. I mean, if an AI tells us the universe is, say, 26.8% dark matter, that's great. But we have to know what patterns in the map led it to that number. If we don't know that, it's not really science, is it? It's more like a magic trick. So this is where a really cool breakthrough comes into the picture. It's something that finally resolves this conflict between our slow but understandable statistician and the fast but totally opaque oracle. It's a new kind of AI, one that's designed to be a glass box.
All right, it's called C3NN, which stands for the Cosmological Correlator Convolutional Neural Network. Yeah, I know that is a mouthful, but the really important phrase in there is physics-informed. See, this isn't just some generic AI that you could use for anything. This network was built from the ground up, with the laws of physics and cosmology literally baked right into its design.
So how does it actually create this glass box? Well, first off, it's heavily constrained. It's like it has guardrails. Instead of just letting the AI go wild and look for any old pattern it wants, it's forced to look for the same specific patterns as the statistician, the pairs, the triangles, the quadrilaterals. And because of that, we know exactly what it's measuring at every single step. It also has fundamental physical principles built right in, like isotropy, which is just the idea that the universe looks the same in all directions. And the result? You get something that can efficiently compute up to 4-point statistics and even beyond. It's the power of AI combined with the clarity of classic statistics, the best of both worlds.
Okay, that all sounds fantastic in theory, right? But does it actually work? This is where the rubber meets the road. To find out, the researchers put C3N to the test on thousands of simulated universes. Each one had slightly different physical laws, and the AI's job was to see if it could figure out the properties of each universe just by looking at its map.
And the key idea here is pretty simple, really. The more information you have, the more certain you should be about your answer. So by including not just the simple pairs of points, but also the triangles from the 3-point stats and the quadrilaterals from the 4-point stats, the AI should be able to really narrow down the possibilities, to home in on the right values for things like how much dark matter there is or what dark energy is doing.
And wow, the results are, well, they're kind of staggering. Just by adding in the 3-point statistics, the triangles, the AI's overall certainty about the universe's properties improved by more than 96%. And then adding the 4-point statistics on top of that gave it another 34% jump. This is a clear, step-by-step, massive increase in what we can know, and we can actually see it happening.
And you can see that massive leap in performance right here on this chart. The C3N is successfully pulling out all that hidden information from the triangles and the quadrilaterals, and it's turning those complex patterns into much, much more precise science.
But wait a second. How do we really know it's actually using those triangle and quadrilateral patterns? Right? I mean, couldn't it just be finding some other weird shortcut in the data that we don't understand? That's a fair question. And to prove it wasn't cheating, the researchers came up with a really clever test.
It's a phase reshuffling test. And what they did is they took the original cosmic maps and, well, they essentially put them in a blender. This process totally scrambles the image, and it completely destroys those complex shapes we were talking about. The triangles, the quadrilaterals, all gone. But, and this is the important part, it leaves the basic 2-point information, the average spacing, totally intact. So, like the slide says, you have all the same ingredients, just a completely different recipe.
And this is the real aha moment. When they ran the AI on these scrambled up maps, what happened? All that extra information it was getting from the 3-point and 4-point functions, it almost completely disappeared. Poof, vanished. This is the proof. It shows, without a doubt, that the C3NN was genuinely seeing and using those real, physical, complex patterns in the original maps. It wasn't cheating. Okay, so let's zoom out. What's the big picture here? Because this really isn't just about one new, clever tool for cosmology. This points to a whole new way of doing science with AI.
So here's a really interesting twist. In the first round of tests, when they compared C3NN to the classical method, the improvement was, honestly, pretty small. The researchers were a bit stumped, but then they realized the problem wasn't the AI itself. It was its appetite. It was simulation limited. It was just plain data hungry and needed way more examples of different universes to learn from. So what did they do? They doubled the number of training simulations they fed it. And the result? Get this, a staggering 347.7% increase in performance compared to that original data-starved model. This huge jump proved it. This glass box AI has absolutely enormous potential. But just like any powerful tool, you've got to give it enough raw material to work with.
And this really brings us right back to the core idea. By building what we already know about science directly into the design of our AI, we're not just making better prediction machines. We're creating tools that kind of think in a way that lines up with our own physical intuition. And that makes them way more powerful, way more trustworthy, and at the end of the day, just so much more useful for actually discovering new things.
This work really shows us a path toward that future. It asks us to just imagine what becomes possible when that split between the careful statistician and the powerful oracle finally disappears. Just think, what new secrets could we uncover about our universe if our most advanced tools were no longer these mysterious black boxes, but were actually true, transparent partners in discovery?